All right, good afternoon, everyone. So we're going to start new unit today, second to last unit on principal component analysis. So let's talk about the motivation first, or at least one motivation. Motivation is that sometimes we have data with high dimensional features. So D for us is the number of features in our data set. Sometimes D can be very large. So in some cases, we'd like to reduce that dimension D. Maybe we're doing this because we're going to be designing a classifier or a predictor, and we want to make the computational effort of doing that smaller. Sometimes we just want to save memory or storage space. So like we have a large database of images, we want to compress those images. We're familiar with other ways to do that, like JPEG, things like that. Yet a third example is if you want to visualize structure in data. When the data is very high dimensional, it's very difficult to visualize it. Humans, we can only see things in 1, 2, and 3 dimensions. So by reducing the dimensionality of the data, we could possibly visualize it if we got it down to 2 or 3 dimensions. So that's sort of the motivation for what we're talking about in this unit. And the specific methodology we're talking about is PCA. It's a very classic idea. And we can summarize it by saying it's the RSS optimal linear dimensionality reduction. So RSS is a familiar thing. Linearity is a familiar thing. We're seeing them together again here. But rather than doing prediction, which is what we did back in Unit 2, now we're doing dimensionality reduction. So that is sort of a new application, a new task in machine learning we have not talked about. That's the new task here. Towards the end of the unit, I'll also describe a couple other contemporary visualization techniques, TSNE and UMAP, just to be complete, although they don't really fit within this linear RSS optimal framework. Okay, so the data set, we have in this case a data set of features, these xi vectors. Like always, each one of our samples has D features, so the x vector is length D. And like always, we can stack them as rows of a matrix capital X. It's not essential, but we will assume that we have already centered the data. So if you sum all those feature vectors over the data index I, they would sum to 0. But this is not essential. You can do PCA without doing this. It's just how these notes were constructed. So the important thing here that you'll notice is there are no targets or labels. So that's the big difference between everything we've seen until now. In the course, we always had XY pairs. Now we don't have any Ys. Or if we do have them, we're going to ignore them. So we're just going to have the X's alone. So that's a big difference. And this is an example of unsupervised learning. Everything we've talked about until now in the course has been examples of supervised learning, like classification and regression. So these last 2 units, this dimensionality reduction chapter and then the next chapter on clustering, these are unsupervised machine learning techniques. There's essentially no labels. So the whole point here is, if we have this very large feature dimension, can we reduce it? That's the whole objective here. Are there any questions on anything we've said so far? Okay. So let's talk about just an example data set that we'll be using in this unit. So images or images of faces, these can be high dimensional. When you look at today's image databases or image data sets, it's not unusual to find images with almost 1 million pixels in them. So we're not going to be working with such high dimensional images. We're going to be working with an older data set from 2007. These images are 50 by 37, so actually they're quite small. But still, 50 times 37 is 1,850. So the question is, do I really need 1,850 separate numbers to describe one of these little faces? Or can I somehow compress it and get a pretty good face from a fraction of 1850, some very much smaller number? So that's what we're going to do. We're going to try to compress these faces. So this is, the data set is called Labeled Faces in the Wild. And this is actually built into sklearn. If you look at the whole data set, you would find 13,000 images. These images all come from news stories in the 2000s. So some example faces down here. You have people like Donald Rumsfeld, Colin Powell, George W. Bush, Gerhard Schroeder. We're not going to use all 13,000 examples here. We're going to, when we load the data, require that we have at least 70 faces per person. And once you constrain it that way, we're going to get a subset of 1,288 images. That's enough for us. So again, image size, 50 by 37. There's 1,288 samples that we're going to download. And it turns out that there are labels in this data set. So you can see the label is really up here. We're not going to use the labels to do PCA, but we can do an experiment later where we use these classes. We can try to do classification, where we can try, given the face, can we predict whose face it is? And we can do that with our PCA approximated features to see how much it hurts us. So that's an experiment we'll do later. But right now, the number of classes is not that important. Okay, so that's the data set. Any questions on this? Okay. All right, so the rest of today's lecture is a bit heavy in terms of linear algebra. So basically what we want to do is you want to try to derive PCA. First explain it, then derive it. So it takes a few slides to do this. So let's first describe what is PCA. So there's basically two main ideas. So the first main idea is that we have a linear approximation. So in terms of equations, this is how it goes. So we are given a whole bunch of these xi vectors. We are going to approximate them using a tall matrix B and a short vector z. So let me draw it like this. So this would be like xi is approximately equal to tall matrix B times a short vector zi. Okay, so xi, as always, has length d different raw features. But we are going to represent xi by zi. That's going to be our compressed feature vector. That is going to have dimension capital R. Okay, so ideally, we want the capital R is much less than d. We want to do a lot of compression. Hopefully this picture kind of illustrates the idea. We're trying to describe all these numbers with just a few numbers. And in particular, the way we're doing that is we're saying this can be approximated as a linear combination of the columns from this matrix. Because that's what matrix vector multiplication is, really. It's saying I have a bunch of fixed columns here. These are just going to scale and combine each of those columns to get this, right? So that's the main idea. So it's linear in the coefficients, zi. So you could say that we're doing a linear compression. This is not going to be fantastic quality. It's not going to be like JPEG. JPEG is nonlinear. It's much more sophisticated. It can do much better than PCA. PCA is classical something we can derive on paper, kind of like how linear regression is a simple technique. We could derive it in closed form. It's not going to compete with the best neural network. We don't expect it to, but it's something we can study. That's how PCA is. It's something we can study. It's really important from the ideas perspective. It's not super high performance. It's just a linear compression scheme. We'll often think of this matrix B as a dictionary, the columns of it as a dictionary. So we have like a dictionary of columns. What we can do for every xi is we can come up with some linear combination of those columns to approximate xi. Okay, so those are the main ideas here. So before we get into the details, are there questions about this first part, about our approach? Is this making sense? Let's see, I want to make sure that this is making sense before we go forward. Are there any questions anyone has? Yes.
You mentioned JPEG, so that uses kind of like a wavelet transform, right?
It does, but it's,
So
yeah.
if that's more refined, how could you apply like a wavelet transform to this?
So JPEG involves a wavelet transform, but it's not, I mean, there's a lot of other stuff going on. So, but like you could say, well, why don't I make, so a wavelet transform is really just a matrix. It's just an orthonormal transform. It's just an orthonormal matrix. So you could say, well, why don't I just like choose B as the columns of a wavelet transform? So then the question is, well, which columns do I use? You know, which ones do I select to try to match all the xi's in my data set? Because that's the data I have. I just have a whole bunch of examples of xi. So here we're looking for like the best subset of columns here. I can have a total of R of them, but no more, capital R. So that's the freedom I have to choose those R columns so that I can do linear approximations of those, and that should be close to all my xi's. So that's sort of the goal. Yeah. JPEG has a lot of other stuff going on, a lot of nonlinear steps in the in how it's, at least how it's designed. Yeah. Yes.
So if our goal is to go from these xi vectors to these ci vectors, how are we guaranteed that this process isn't being invertible?
It's not invertible.
Okay.
This is what we call lossy compression.
Okay.
So this is an approximation.
Okay.
It's not equality. Right. So what would be an example of an xi vector that would not work here? No, zero vector would be perfect because I can just set my z's to 0 and then I get 0 perfectly. So if I already came up with my dictionary and you wanted to find a vector xi that would give me real trouble, how could you construct it? If I said, this is my B, and you said, okay, I'll show you why your B is not good. How could you choose X so that it wouldn't work at all?
Your elements outside of B.
Yeah, outside of what exactly? The column space, yeah. So the set of all vectors that we can construct in this manner is called the column space of V. It's the set of all linear combinations of the columns of B. So if I wanted to give this method trouble, I would come up with an xi that was completely outside the column space. Now there's no way I can describe it with this method at all. Okay. So now we're getting to understand a little bit about what we're doing. Yes, we have freedom in constructing B. But once I construct it, I need this single B has to work for all the xi's in my data set. So if my data set is really diverse in a way that there's no way I can do that with any R columns, where R is a small number, then I'm in trouble. Then this is not going to be a good compression. The hope is that if I choose R large enough, that I can fit all my data pretty close to the column space of B. I can reach most vectors. Yeah, there might be a bit of error, but it's not going to be terrible. And maybe in doing so, I'll save a lot of coefficients. I will have coefficient vectors of length R instead of length D. That's the goal. Okay, so is this starting to make a little bit more sense, what we're doing? Okay, all right, any other questions? Okay, so the next thing is, well, now exactly how do I come up with B and Z? Well, my goal is to minimize the RSS. So the xi's, these are given, but I have complete control over designing both B and all these zi vectors. So for each of my xi vectors, I'm going to have a single zi vector, but then this B matrix is sort of common over all my data set. Okay, so I have an optimization now. This is our familiar RSS, sum of the squared Euclidean error. But my optimization is jointly over the dictionary B as well as these code vectors or coefficient vectors zi. And this is what we call principal components analysis. Okay, so this criteria here is chosen for simplicity, for tractability. It's not necessarily the best thing to do. In fact, I'll show you some nice, simple illustrations of why this can be a terrible thing to do if your goal is to eventually use these approximations to do something like classification. So if you're doing PCA first to compress your data and then doing something later with that compressed data like classification, this could be terrible. It can work okay. We'll also show an example of where it works okay, but it can, in certain cases, be terrible. So you have to be careful in using this. This is just a tractable idea. It's not necessarily the best thing for any given application. So, but at least as we'll see in the next few slides, this is an optimization problem that we can solve. It does take a bit of work, but we can actually solve it on paper and figure out exactly what these optimal B's and Z's are. Okay. All right, so those are the main ideas behind PCA. Most of the rest is just a lot of linear algebra, a lot of tricks. All right, so any questions on high-level stuff? Okay. All right, so let me give you a summary of the solution, and then a derivation. Okay, so the solution that we'll find after a bit of work is that the optimal B, we'll call it B hat, is constructed of a matrix of, we'll call it capital V, and this matrix has vectors little v's. These little v's are what we call the principal eigenvectors of the sample covariance matrix Q. Okay, so we know how to construct the sample covariance matrix. Since our data is already centered, this is what it is, right? We've seen this several times, I think, at least, right? We've seen this. So if the data was not centered, we would need to subtract out the mean from these xi's. But since it's already zero mean, this is the sample covariance matrix. And essentially the eigen decomposition of this matrix means we can rewrite this is how we construct it from the x's. We can rewrite it in a different way. We have eigenvalues and eigenvectors. So we'll talk more about this, but when you look at those eigenvectors, in general, there's going to be bigger ones down to smaller ones. And each one of these eigenvectors, lambda j, has a corresponding vj. So if we just focus on the R biggest lambda j, and we look at their respective vj's, that is what we're going to construct this matrix out of. So when we say the principal ones, they're like the most important ones, the ones that correspond to the largest eigenvalues. So that's how we build B. And then the way that we build the z hat i's, the optimal z's, is we take this same matrix, but now we transpose it and multiply it times the sample xi, and that gives us z hat I. Okay, this is not obvious why this is true, so that's going to take a little bit of explanation. But at least we have a couple visual examples. So here on the left, I have a bunch of data points in R3, three-dimensional features. And in particular, the data points are these circles. The green and red circles are not like in different classes or anything. It's just this picture is showing the red ones are below the plane, the green ones are above the plane. But you can think of them all as the same color. Maybe that's the best. So, I have a bunch of data. And in this example, I'm asking, can I compress that data so that every data point can be expressed by two numbers rather than by three? Because in the original coordinate axes, I have like x, y, z, if you will, or x1, x2, x3. But what we're saying now is with PCA, we're essentially going to come up with an approximation that sits in a plane. So the dictionary would be composed of any two vectors that define that plane. And then the zi's are the coordinates in this new space. So the zi's say within this new space, where do you find those points? And in particular, the approximations are the closest points in the plane. So let's say this is my original data point. Once I approximate it or compress it, it's now here. So it's not perfect. I've actually changed the data. It's not an exact approximation, but you can see maybe it hasn't moved too far. So in fact, all these lines, these are the approximation errors. The new approximations are all going to be sitting inside that plane. Now we can do, with the same data exactly, we can ask the question, what if I want to approximate the things with a one-dimensional subspace? So that's a line. So now we're asking the question, what is the best line here that is closest to all my data points? And so now the projections, or the approximations, are the closest points in that line. So those are the approximations we get. And once again, these are the approximation errors. Okay, so this is sort of a visual example of what PCA is doing. It's trying to take a data set and approximate it on a subspace where the dimensionality of the subspace is less than the dimensionality of the original data. Once you do that, all you need to represent the entire data set after compression are the coordinates for each one of your data points, the z's, as well as the dictionary itself. You have to know, how to construct the plane. That's the B matrix. So with the B matrix and a bunch of z's, that's now your new description of your data. You don't need those x's anymore. Okay, so that's what PCA is doing. So, is this making sense? Okay. So, well, I don't know if this part should make sense because it's just pretty opaque until we go through it, but hopefully at least this part makes sense as to what we're trying to do and what's happening in some visual examples. All right. Okay, so yes.
Just real quick for clarification, like Z, in terms of the graphical representation, B is the plane, right, that we created, is that what you're vector?
Yeah. So the columns of B would be sitting in the plane and actually defining the plane. Right? Like if I have two vectors in 3 dimensions, if you give me any two vectors in 3D, I can make a plane, right? They define a plane actually. And in fact, I could do things like rotate those vectors within the plane and it's going to be the same plane. So there's a lot of ways to get that plane. So that's what the B is.
Yep.
And then given that B, it's how do I take a linear combination of this and this to get any point? So I just need two numbers there, linear combination of the first times the second, and from that I can construct any point in the plane.
Okay.
So each one of these guys gets a two-dimensional representation in the plane. Now when we're over here, there's only one vector that is describing the dictionary. It's the vector pointing in this direction. And so now for every data point, there's just a one-dimensional coefficient that says how far along this line do I go. So this guy is this far along, this far along, this far along, and so on. So now I have a one-dimensional, my matrix just has one column, and each of my zi's is a scalar. Okay. All right, so it's making a little more sense? Okay, great. Any other questions? Okay, so let's dig into the derivation. So the derivation at a high level, there's two steps. First, we're going to figure out what the z's are. The z's for any arbitrary dictionary B. Second, we'll figure out what the dictionary is. That's going to be a lot harder. Okay, so in the first step, actually the first step's pretty easy. The first step involves this problem. So we said we're going to fix B. In fact, let's take just a little step back. So this is the overall thing we're trying to do. This is our overall problem. So imagine now that I'm fixing B. So that's no longer something I optimize. And let's also imagine that I'm optimizing one particular zi. Let's say like Z1. If I'm optimizing Z1, then from the way that this is constructed, I don't really care about Z2 or Z3, right? They're not involved in the optimization because they all add a different norm to this overall sum. So if I just want to optimize Z1, I can forget about this. I can just look at X1 and Z1, right? So in other words, if I want to optimize ZI, I can just worry about this without any sum on it. I have one particular I I'm working on. So that's where we get this. So this is what we're interested in doing. And if you stare at this hard enough, you'll realize this is a problem that we already solved back in Unit 2. The terms were different. Back in Unit 2, we had yi, we had a, and we had beta I. But mathematically, it was, except for those variable names, it's identical. And we saw that this is the solution. We derived this. How did we derive it? Does anybody remember how we derived this? What was our technique to getting from here to here? Yeah, we take a derivative, right? We take the derivative of this with respect to all the different zi's and we set them to 0. And we basically solve a linear system of equations. Okay. So that's done. So at least this first stage, because of our work back in Unit 2, we know how to do this. And in particular, this is exactly what we get. This is the optimal z hat I. So now that I know that, I can go back to this expression, and I can literally plug that in for all the different i's, and then the only thing left to optimize is b. So that's what we have over here. We plugged in this expression from above for the zi's. Now the only thing left to optimize is b. Okay, this expression looks a little bit more challenging though, because b shows up 4 times here. Some are transposed, some are inverted, and so on. So that's the work we have ahead of us to figure out how to do this. Okay, so, but along the way, we need to sort of pause and view things in different ways to understand things better. So one thing we can do, maybe it makes our life a little bit easier, maybe not, is to recognize that here it looks like we have 2 separate terms that are involving xi, but we can actually rewrite this to have a single matrix multiplying xi inside this norm. And so that's just by recognizing that I can write this as I times xi. At that point, we have a matrix here that has an interesting structure. And this is actually something that maybe some of you have seen before in other courses. But this is what's known as an orthogonal projection matrix. In fact, this one is also an orthogonal projection matrix. So let's talk for a bit about what we mean by that. Okay, so here let's talk about what we mean by orthogonal projection. So first, let's talk about sub-column spaces again. We mentioned this briefly here we see it written down. So if I have a matrix B, and I say, what is the column space of that matrix? It's the set of all vectors that are linear combinations of those columns. So it's the set of all B times Z's, where Z's can be any vector. In this case, B has R columns, so Z has R elements. So it's just the set of all possible linear combinations of those columns. So in terms of a picture, if I have two vectors, so let's say this is for R equals 2. So now I have the two columns of B, like B1, B2. Then all linear combinations of those form a plane. And now, so this is an example where I have a three-dimensional world, but I have a two-dimensional subspace or plane. So now let's say I have a vector x in that three-dimensional world, so that's this guy. And I say, what is the projection of x into the plane? So it's sort of like, imagine that there's a sun shining from above, and it's causing a shadow in the plane. If the sun is directly from above, that shadow is the projection into the plane. Another way to think about it is, what is the absolute closest point in the plane to this x? So if you wanted to find the closest distance, you would go down here, and you would want to sort of project this onto the point that is orthogonal to the plane. Because if I move this over a little bit so that it's no longer orthogonal, that means that it's not as short as it can be, right? I could move this way, and the line gets a little shorter. Once you're directly orthogonal to that plane, you can't move it around to make this any shorter. So the shortest distance to the plane has this, you could say it's the error that is orthogonal to the original x. So I think that's probably something you guys have seen before somewhere. Have you seen this orthogonal projection? And in fact, we solved this problem here. This is sort of like saying, someone gives us this. We want to design this so that it's as close as possible to x in the sense of Euclidean norm. And in this case, B was just given to us, right? So B is defining the plane, and now we're asking, well, what's the closest point in the plane? It's actually this. So you can see that to get to that point, so this is the z hat. So now if I want to know what is B times z hat, that will be B times B transpose B inverse B transpose xi. Okay, so this thing, B times B transpose B inverse times B transpose x, that is the closest point in the plane. That is this. Okay, so basically what we just discovered is that projection can be implemented by a matrix multiplication. You take your origin point x, you multiply by this matrix of this form, and all of a sudden you are in the plane at the closest point to your original x. So this is what we call orthogonal projection. It's orthogonal in the sense that there's this orthogonality between the error, everything that in x that was not in the plane, and everything in x that is in the plane. Those two things are orthogonal. Okay, so is this part making sense? Essentially, we solved this problem, and now we're sort of visualizing it over here. Okay, so then we have, that's x hat, that's the closest point to x in the plane, but we also have this error vector, e. That's everything that we're leaving behind when we do this projection. That's all the error. And just by the way these are constructed, this E is some other matrix times X, and that other matrix is just I minus this PB. So that's where we got this notion here. This is I minus PB or PB perp, and then this is just PB. So PB basically means projection onto the column space of B, and this means projection onto what is orthogonal to the column space of B. Okay, so that's orthogonal projection. I'm thinking you saw this in a linear algebra course at some point, maybe another course too. But that's, clearly related to what we're doing here with PCA. And some of the main things we want to realize is that these matrices, these orthogonal projection matrices, have some important features. So one important feature is that they're symmetric. And you can see the symmetry just from the way they're constructed. Right? If you take the transpose of this, you get the same thing. Because remember, when you transpose, you have to swap the order of everything and transpose everything. So I move the B transpose over here, and then I transpose it again, I would get a B. I move this one to the other side, I transpose it, I get a B transpose, and so on. This is already symmetric. So basically, PB is PB transpose. It's symmetric. The other important property, and actually the only other important property of an orthogonal projection matrix, is that it's idempotent. Idempotent means when you that quantity is equal to its square or cube or fourth power, like this. Okay, so why is that the case? One way to see it is just to take the, by definition, you have like B times B transpose inverse times B transpose. And now let's multiply that times the same thing again. So we get B times B transpose inverse B transpose. And you immediately see that this cancels this inverse. Okay, so those are gone. And what you have left is just the original thing here. So you can also see that from the form. But there's another way to think about it, just more intuitively perhaps. The idea is, if I think about PB as an operation that I perform on a vector, so I start with this vector x. I perform the operation which projects me into the plane. Now let's say I perform that operation again on this projected point. Well, if I'm projected in the plane and I project again, I just stay in the same space. I don't move. I'm already in the plane. Projection doesn't do anything. So this is like saying projection once is the same thing as projection twice. You do it once, that's all there is left to be done. Okay, so those are basically the two important properties of projection matrices. There's some other interesting properties too, not essential to us, but if you look at the eigendecomposition of PB, you'll find that it has R eigenvalues exactly equal to 1, all other eigenvalues exactly equal to 0, and PB perp is sort of the opposite, R eigenvalues equal to 0, all others equal to 1. But these ones at least will be important ingredients in our derivation. Okay, so that's orthogonal projection. Questions on these ideas? Yes?
If I apply one projection on a different progression, would I end up getting, or projection, would I end up getting the zero matrix? Because I can't project into an orthogonal direction, or is that not the case?
So I guess, so you're saying you have like two different column spaces, like B1 and B2 or something, and you do projection on B1 followed by projection on B2? Is that what you're saying?
Just multiplying two different projection matrices, I guess.
Okay.
on the same space.
Yeah, so if those matrices share a subspace, then projection will, respect that subspace. But if there's like some subspace that is in the null space of one and the column space of the other, then yes, when you do the product, that goes away.
Okay.
Yeah. Okay. All right. So coming back, how does projection affect PCA? Well, this is the problem we were working on. This is that matrix I minus, B times B transpose B inverse times B transpose. So just writing it in a more clean way. Well, we just saw that this is the projection error associated with the ith point. So that means in this picture, that projection error are those little lines here. And so this is saying the sum squared norms of those little guys here. So we want to figure out where to put the plane so that the sum squared error is minimal. Right? Makes sense. So how does this picture differ from what you saw back in Unit 2? You had similar pictures, but they were a little different. Does anybody remember how?
You're dealing with a plane instead of a dividing line, basically?
No, so you're thinking classification. Unit 2 regression, we had a plane. So what's the difference between those pictures and this one? Does anybody remember?
In Unit 2, what we did was we took the vertical distance
Exactly.
from the point to the line, but here we're taking the...
Exactly. They were the vertical distances. We had similar pictures in Unit 2, but they were vertical distances because we were measuring the error in some y space. So what's different now is we don't have any labels. So we're just saying I have these points in x space. I want to approximate them with the subspace. So it may seem like there's some similarities, but there's also some pretty big differences between what we did back in Unit 2. Okay, but anyway, so now we can see PCA chooses that dictionary B to minimize the sum squared projection error. Okay, so hopefully we have some intuition about what we're trying to do at this point. Are there any more questions about the visualization or the goal? Okay, the next thing then is just to kind of dig into the linear algebra. And we'll see there's just a bunch of tricks that you will see in many other derivations, so it's good to see these tricks and to learn them if you haven't seen them before. Okay, so this is where we start. Let's give this guy a name. This cost we're trying to minimize, we'll call it JB. So this is what we want to minimize. So the first thing we can do is say, all right, we have a norm squared. So if I have like a vector A inside a norm, that's like saying A transpose A. So let's do that, where now A is this quantity, and we get this. Okay, so from here we say, okay, PB perp transpose, well, because this is an orthogonal projection matrix, the transpose is really not doing anything because it's symmetric. So we can just imagine getting rid of the transpose. The next thing we say, oh, okay, actually, this is like PB perp squared. But squaring doesn't do anything. So I can actually just replace that with PB perp alone. Okay. The next trick is to say, all right, this is a scalar. Right? It's a row vector times a matrix times a column vector. This gives a scalar. So I think we've seen the trace before in this class. The trace is defined as the sum of the diagonal elements of a matrix. So you have a matrix, you sum up the diagonal elements. Well, when I have a scalar, there is only one diagonal element, so the trace is equal to the scalar itself. So since this is a scalar, I can replace it with the trace of itself without changing anything. So that's what we're doing here. Now the reason we're doing this is because the trace has this amazing property that you can reorder matrix multiplication inside a trace. So obviously we know that in general we cannot do something like write this way. In general, A times C is not equal to C times A, right? This is true with scalars, but it is not true with matrices and vectors. However, once those things are inside a trace, you are allowed to do that. It's kind of crazy, but it works out. So we can now take advantage of that here, and we can take the second half and move this around to put it in front of this xi transpose, and at that point we get this. So now we have a matrix times a column vector times a row vector. When we multiply all that out, we get a matrix, and this says when you take the sum of the diagonals in that matrix, you get back this term. All right, everybody with me so far? Now the reason we're doing this is because this allows us to bring the summation inside. So the trace is linear, so the sum of the trace and trace of the sum are the same. So I can move this inside, and I can even move it past this because this is another linear matrix multiplication and it doesn't involve I. So I can bring the i's all the way up to these xi's, and now I can sneak in a 1 over n inside there as long as I compensate with an n on the outside. just to get this in the form of our sample covariance matrix. And remember that that was one of the important ingredients in the PCA solution. The PCA solution was about the eigenvectors of that sample covariance matrix. So now we see why that might be. Sample covariance matrix is right here. We'll call it Q. Okay, so so here's a couple important facts about the sample covariance matrix. First of all, this is what's called a positive semi-definite matrix. So a positive semi-definite matrix is a matrix that obeys this property. It says you can take any vector x, and if you form a quadratic form by multiplying q on the left and right by x, this is guaranteed to never be negative. That's what it means for this to be positive semi-definite. And so, why are sample covariance matrices positive semi-definite? We can do a short proof. So let's start with this. For any x, we plug in the expression for q. We can then move this x transpose through here and realize that we get x transpose times xi. That's a scalar. So let me just put a little parentheses around it just to clarify that we're thinking about isolating this. And then over here we have another thing, xi transpose x, which is another scalar. Well, actually, these are the same things, right? Because since they're scalars, we can transpose them without changing anything. And if I transpose this one, what it does is it moves the I from here to here. At that point, you can see these are actually the same. So this is that quantity squared. And now it's sort of clear. If I have the average of non-negative quantities, then the result will also be non-negative, right? Can never go negative by averaging non-negative quantities. Okay, so here, hopefully we see now, yes, sample covariance matrices are always going to be positive semi-definite. The reason we care is that all positive semi-definite matrices have an eigendecomposition of this form. So we have matrix V times matrix lambda times matrix V transpose. V is what's called an orthogonal matrix. This is a matrix whose columns are all orthogonal to each other, whose rows are all orthogonal to each other, whose columns are all unit norm, and whose rows are all unit norm. So it's a very structured matrix. It means that if you do V times V transpose, you get identity. But also if you do V transpose times V, you get identity. So this is a very interesting matrix. And the lambda is a diagonal matrix where along the diagonal of this diagonal matrix, you have entries that themselves are guaranteed to be non-negative. They're never complex value, they're never negative, they're always 0 or positive. So any positive semi-definite matrix you encounter is guaranteed to have a decomposition like this. So that's going to be super important for us. And although if you do this in MATLAB or NumPy, if you do one of these eigendecompositions, the software is not guaranteed to give you sorted eigenvalues, but we're just going to assume that they are sorted because that's always something you can do as another step. So we're going to sort them from large to small. It could be that some of them are equal sized. That's okay. But let's just assume that these are sorted from large to small. Okay, so the theorem now, we're ready to state it, is that, okay, this is where we are. We're trying to optimize this n trace PB perp Q. So this theorem was proven in 1936, that if you solve this, you can solve it using the R principal or most important eigenvectors of Q. So we're stacking those eigenvectors to make a matrix, calling that matrix capital V. That is the optimal dictionary, the thing that minimizes this. And to be totally technical, you can change, this is not the only matrix that works. If you take this matrix and you multiply it on the right, so this is a tall matrix, if I multiply that on the right by any full rank square matrix there, I will not change the column space, and that will also work fine. You just need to correspondingly change the z's. But for our purposes, we'll just take this kind of canonical solution, which is to say, compute the r most important eigenvectors of Q, and that is going to be the dictionary. Okay, so that's the last part of our proof is to go through that. Let's see. I think I can do this pretty quickly. So this is what we want to minimize. So we can now expand PB perp back into I minus PB. And now we can write this as I times Q minus PB times Q. So that gives us this because the trace is linear. And if we're optimizing B, we don't really care about this term. It doesn't depend on B. So if I want to minimize this cost, I can equivalently maximize this term. I can maximize the trace of Q because of this minus sign. So instead of focusing on a cost, let's focus on a utility, which is sort of the opposite of a cost. So let's maximize this. Okay, let's plug back in Q. Q, we're going to use this eigendecomposition, V lambda V transpose. Now we can play our game with the trace. We can move V transpose to the front like this. And now, if you look at this carefully, let me try to draw it. So we have a matrix here, and we have another matrix lambda. So lambda is the one on the right, everything else is the one on the left. We know that lambda is diagonal, so it has zeros everywhere except for on the diagonal. Now this other matrix has entries everywhere. But let's think about what happens if we multiply this times this and then take the trace. Which of these elements matter? Okay, so if I multiply these two matrices, this first term will multiply this column, right? Scale the entire column. But when I take the trace, I'm actually taking just the sum of the diagonal elements. So I don't really care about all these. The only thing I really care about is this diagonal element. That will get scaled by this, and that becomes one of the terms in the trace. Then this second diagonal element will get scaled by this, and that becomes the second ingredient of the trace, and so on. So the only things I really care about here in this this left matrix are the ones along the diagonal. Okay, so and we will call those the alphas. Alpha j are going to be the terms along the diagonal of this matrix. And then we already called these the lambda j's. So finally, at the end of the day, the trace is the sum, as you go down these diagonals, of the alpha j times the corresponding lambda j. Okay, so here's alpha j is, you take this matrix and you extract the jth row and jth column. That's what alpha j is. Okay, is everybody with me so far? All right, so we can actually simplify this a little bit. So if you remember that this matrix V had columns that were little v's, and here on the left we have rows that are the little v's. And so if I'm looking for the jth element of this overall thing, I'm going to get that by taking the jth one of these, multiplying this matrix times the jth one of these. So that is actually what I'm going to get for alpha j. I don't have to consider the entire V matrix, I just have to consider the jth element of it. Okay, so that's the alpha j's. There's a couple important facts about the alpha j's. Let's first take our alpha j and sneak in PB transpose. The reason we can do that is, remember, number one, PB is idempotent, meaning PB equals PB squared. And then PB is also symmetric, so I can change this other PB to PB transpose. It doesn't change anything. And we're going back in this direction to realize that this is, so I have basically a row vector times the same column vector. That's the norm squared. And finally, what is this thing inside the norm? It's the projected version of Vj. So when you think about projection, projection is never going to increase the norm of a vector, right? If I start with this vector here and I project it, notice how the length or the norm decreased. the best that can ever happen in terms of not, not shrinking the norm is if I start already in the plane and I project it, then the norm stays the same. But I can never increase the norm with projection. And so that is why I'm saying that we can upper bound this by the norm of vj squared. And finally, if you remember, these guys are all unit norm. So this is all equal to 1. The other thing you can see is that alpha j can never go negative. It's a norm, so it can't be negative. So that means alpha j is between 0 and 1 individually. The other important thing is that when you sum up the alpha j's, you get exactly r. So why is this? So let's first remember how the alpha j's are defined. So if I sum them up, that is the same thing as taking the sum of the diagonals of this. In other words, the trace of that. So we have the trace of this. Now we can play the game with the v, move it to the left. Now we can play the next game is that v times v transpose is identity, so that goes away. Now we have trace of PB. We plug in the PB expression like this. We play the same trace game where we move this to the left side, and we get this. And now you can see that I have a matrix times its inverse, so that gives identity. And this happens to be an R by R identity matrix, so when I take the trace of that, I'm just counting up 1 plus 1 plus 1 R times, and I get R. Okay, so finally, at the end of the day, we can state our optimization problem like this. We want to find these alpha j's. We know that all the alpha j's are between 0 and 1. We know when we add them together, we get R. And what we want to do is we want to choose them to maximize this. Okay, although this sounds like a really complicated problem, it's something that you might do when you walk into a store. Let me describe it this way. Suppose that you walk into a store and there's these different items indexed by J on the shelf. And you have to buy between 0 and 1 units of each item. Let's say for each item there is no more than 1 on the shelf. So you can't buy more than 1. And obviously you can't buy less than 0. And let's say you are forced to buy R items total out of D. And finally, you get a reward of lambda J when you buy item J. So lambda J is like your happiness factor. So this item makes you a little bit happy. This item makes you a lot happy. Okay, you have to buy R total items, at most 1, at least 0 of each one. Which items are you going to buy? You're going to sort your items into the ones you like best, and you're going to buy 1 of each of those. Not less, right? Because if you buy less of your favorite item, that means you have to buy something that you like less than your favorite item. So you're just going to find your top R favorite items, buy 1 of those, buy whatever the store has, and walk out. So that's it. So this is the optimal solution. Alpha J, which is how much we're buying, we're going to buy 1 unit if J is between 1 and R. So this is, remember we ordered the lambdas from biggest to smallest, so they're already ordered from favorite to least favorite. And I'm going to buy none of the items, none of the alphas for something that's not in the top R. So basically, that is the solution to this problem. And with that, we're almost done. So essentially, the alpha j's were these terms. We know what we want the alpha j's to be. And the way that we can do this is if I choose B as this VR matrix, which is these eigenvectors stacked like this, and if I make, so the corresponding projection matrix of this will be VR transpose. And if I stick this inside here, then it's pretty straightforward to verify that when you look at this quantity for the different j's, you get 1 if Vj is in this matrix, or 0 if the Vj was omitted from this matrix. Okay, so sorry to go over, but that's it. So that's just a summary. We've proven what we wanted to. I think the very last step is how to get, let's see, did I do how to get the ZJs? Well, I feel like I'm over time. I don't want to take you longer, but I can finish that up next time. But essentially, this is the hard stuff about PCA. Now that we've gone through the hard stuff, the rest of the PCA lecture is fun. We'll get back to those eigenfaces. We'll see some nice pictures of how you can take apart faces into different eigencomponents and stuff. So that will be more fun. And we'll continue that after the break next Monday. So I hope you guys have a good break. And I'll see you. If you haven't picked up your midterm, please come and pick it up for me so I don't think that you're absent. All right. See you guys next week.